Okay, so that helps. Thank you. Okay, so that's the radius. One in terms of yeah, sine is your distance above the horizontal axis, and then cosine is your horizontal distance from the
How many people think they're done? They got the whole thing filled out. Okay, keep going. Take another minute.
Size of theta is 1. Either or, so it's either. Theta in that case is 90. Like you want to look at the math of theta, you have to be sine
Did you get those? Okay, what do you think for C? What do you think for C? Okay, so I heard, yeah, so if you said 0.8 or 0.9 or something around there, that's a good estimate, somewhere 0.8, 0.9. What about D? Yeah, if you said 1.1, that's a good estimate. About 1 and then a tenth of 1, right? About 1.1. What about E? Little less than a halfway, or half a radius length. So if you said something like these values, so A, B, and F, you can say exactly are 1. Those are radii. That is a radius. So those are 1. Okay, in terms of theta. So in terms of theta. But we're still measuring in radius lengths. So for A, B, and F, we don't need theta. It's still 1. Still 1 radius length. Okay, what about C? How do we measure C, that height, in radius lengths in terms of theta? That's what sine is. We should probably, let's do D first. So what about D? How many radius lengths is D if that angle is theta radians? It's theta. That's where theta radians, that's where the measure of the angle comes from in radians, is how many radius lengths the angle's rays cut off. So this angle's rays cut off if that angle is theta, radians, then this angle is cutting off theta radius lengths of arc length. That's how we define, radian measure. Okay, by arc length, measured in radius lengths. Okay, C, some of you said, sine theta, E. So sine theta then is the vertical height to this terminal point measured in radius lengths. And the cosine theta is this horizontal distance to the terminal point measured in radius lengths. Those are the definitions of sine and cosine. Questions on that? Okay, so now, if the radius is 82 feet, now I want you to write all those lengths in feet in terms of theta. If the radius of the circle is 82 feet. So write all those lengths in terms of theta, but now in the units of feet. Go. You do the same thing for every entry. What do? If these are all radius lengths, and now each radius length is 82 feet, then how are we going to get it in feet? Just multiply each one by 82. So all the radius lengths are 82. Okay, what's the arc length in feet? 82 theta. That's the arc length in feet. And then this vertical height, 82 sine theta, horizontal distance, 82 cosine theta. All right, now use B, E, and C to write expressions for sine, cosine, and tangent of theta. So sine theta equals what in terms of B, E, and C? Same with cosine, same with tangent. So just think of sine is measuring that height in radius lengths. So if we want to measure this height in radius lengths, how can we use B, E, and C to express how high up you are in measure of the radius? C over B. You would take this height in, like, say, if it's feet, and divide by B feet. Cosine? You take E over B and tangent. So tangent is defined as the slope of this terminal side of the angle. So slope is change in y over change in x. Okay, and that's where these relationships, so C is the opposite side, B is the hypotenuse, E is the adjacent side, B is the hypotenuse, and then this is opposite over adjacent. Question on this slide? So that's a crash course on triangle trig. If you understand that, then you've earned your right to use these expressions, these ratios, because they're not just, they just weren't made up out of the blue. They came from measuring everything in radius lengths. That's where trig all starts. Okay, so here is, so those are the three that we just talked about. Oops, go back. Okay, so here are, now you learned these derivatives for these other trig, cosecant, secant, and cotangent. Cosecant is just the reciprocal of sine, 1 over sine. So in the triangle, then it's going to be hypotenuse over opposite. Okay? Cosecant, or sorry, just secant is 1 over cosine. So using the triangle, it will be hypotenuse over adjacent. All right, and then cotangent is 1 over tangent. So using the triangle lengths, it'll be adjacent over opposite. Okay, and then the Pythagorean theorem, measuring everything in radius lengths, we get this triangle that you saw on the previous screen, a right triangle. And so by the Pythagorean theorem, cosine squared plus sine squared of an angle equals 1 squared, and so that's called the Pythagorean identity, and then that's often used to solve for, in a given situation, sine squared or cosine squared would be 1, that should be minus. One minus sine squared. Okay, so these are the only ones you should need for your homework due Wednesday. This is most of what you should need for those. Any questions? Okay, so I want to talk a little bit about the circular pond problem. Just one aspect of it that's something new that we haven't talked about yet. And this is all also in detail on the video, but I think this is important to talk about. So we said that in general, we get this, if we want to minimize time in a situation, then the whole problem is going to revolve around a time function. And we saw that this particular problem was time as a function of this angle theta. It determines the point P that they'll run to. I changed it into like part of a adventure course race. Okay, so they're gonna get here, and they have to get here as fast as they can. So they're gonna run around to P and then swim, but they have a choice, of course, where to run to, and then start swimming from there. So the angle theta determines that point P where they're gonna stop running and start swimming. Okay, and so we said that this function t theta would be the total time spent here to here, so it would be the time spent running plus the time spent swimming. That's the general structure of it. And we built that function for the example Friday, and then all the details are in the video. So we're looking to minimize this function. So we're looking to find a local minimum. So to do that, we find the derivative, and to find local max or min, we do what? Set it to 0, because we know that at local high points and low points, what? The accumulation pauses for a moment. In this case, the accumulation of time. So accumulation pauses, we get a high point, it pauses, we get a low point, so therefore we're looking for where the derivative is 0. We're looking for where the time function doesn't change for a moment. No change, just going to indicate our high points and low points. Okay, so when you do that in this problem, with the new, you get 2 critical points. With the new version that I posted on in the video, you get a critical values of about 1.6, I think it's 6.9, and then you get another critical value of pi. Okay, and so we need to verify what these are in order to figure out if we have min or max. Now pi actually is where would P be for pi? The angle of pi would be all the way here, meaning what situation for the running all the way around. So pi would mean run the whole way. Theta equals 0 would mean swim the whole way. Okay, theta equals 0 means point P is the starting point, just swim straight across. So we have this critical value at 1.69, which is actually about here. And then we get another critical value at pi. So we need to, just because we have a critical value doesn't necessarily mean that it's a local max or local min, the thing we're looking for. We've kind of, to this point, we've kind of assumed that when you did your Weber problems from before. You kind of could just assume that if they're asking for a max in the problem, you set the derivative equal to 0, you're going to get a maximum. Well, we know that it's not true, or not necessarily true, because there's different types of critical values that you have, maxes, mins, etc. So what happens is this turns out to be actually a local max, meaning if she ran to this point and then swam the rest of the way, this would take the most amount of time of anything. right? Or in the local area. So because it's the only critical point from 0 to pi, what we have then is, so looking at all possible values, so the domain of this function that makes sense would be to take values from 0 to pi. 0 meaning all swimming, pi meaning all running, and then everything in between. So from 0 to pi, we get here at this 1.6 value, 1.69, we actually get a local max, not a min. And if there's no other critical values, that means that starting at 0, it has to be increasing this whole way. It has to be increasing all the way from 0 to that local max because there's no other critical points in there. And then starting there, it has to be decreasing all the way to pi because there's no other critical points. Would you buy it? So because that's the only critical point in between 0 and pi, that local max has to be, this has to be always increasing to there and then always decreasing to there. So where is the minimum time going to occur if that's the case?
So it's either you run all of it or
Right, it's got to be at one of these endpoints. If she wants the minimum amount of time, it doesn't occur at a local min. It occurs at the endpoints of the interval. That makes sense. So what happens is if you put, so to test that, you're going to just go to your time function, put in t of 0. You can put in t of 1.69 and then t of pi and test them out. And so what are we looking for? We're looking for the min, the total minimum amount of time to be at one of those two places because we know this is going to be the maximum amount of time. This is the max. So this is an aspect to these optimization problems that we haven't talked about yet. That it's possible that to optimize a situation, it's not going to be at a local max or min where the first derivative is 0. It's going to be at one of the endpoints of your domain. And so to find those, you just take those endpoints, plug them into your function to get that output value, and compare them to the outputs at the critical values to see what's really happening. In this particular case, and you can watch it in the video, it's the fastest for her to swim the whole way. It's the fastest for her to swim the whole way, meaning theta equals 0. Okay, so this is an important point that if the problem, just because the problem is asking for a maximum and you get a critical value, it doesn't mean that critical value is necessarily the maximum. Like we've kind of assumed that to this point. But it could occur at what's called an endpoint of the domain that makes sense in the situation. So you have to put those points into the function, find their values, and compare them to see what's going to be the max or the min. So for another example here, you could suppose you have a domain like this from say 0 to whatever 100. So here's the situation. So say then the function looks like this. And it says, you know, where can we maximize and where can we minimize the value of this function from 0 to 100? Well, you'll find critical points. You'll get a local min there and a local max there. Will those be the answers to this problem? No, the absolute maximum in this realistic interval will be at 0. And the absolute minimum in this situation will be at 100. So you have to check your endpoints of your realistic domain. So that's truly the max, not the one you got from the critical point. And that's truly the min, not the one you got from the critical point. So do you see how that's an issue? So you have to check your endpoints. You have to check your endpoints to see if maybe they are the max and min, the solution to the problem, like this one is. Theta equals 0 is not a critical point, but it gives the minimum time, swimming straight across. Does it make sense? Okay, that's important. Any questions before we revert back to big picture stuff? So we've been taking our knowledge of derivatives and we've been doing lots of these real world problems. We did the related rates problems. We've done these optimization problems. But we want to kind of look back at big picture stuff. And so I'm going to bring us back to looking at accumulation and rate. So here is a rate of change of elevation as a function of distance from the border, say the border of a state. Okay? And so there's three functions, capital R, capital S, and capital A. Should be familiar, or at least somewhere in the back of your mind. And so the above graphs show functions R, S, and A. Delta X is 0.4 miles. And so I have a couple questions for you. See how you do on these. Take a couple minutes. What does a point on the function R represent? The blue step graph S, the function A. So pick a point. Explain what each point represents on each of those three graphs. And then express the change in elevation from starting from 0.8 to 2.2 miles, and I'll make the numbers bigger, in two ways, using S and then using A. And for S, you can use K1, K2, K3 to be the constant values of S. Okay, so I will turn you loose. Go. Okay, I want to see what you have for number 2. Let's see what you have for number 2. Write it down. Tell me what you have for number 2. calculate, just express it. I'm not asking you to try to pick off numbers and do calculations. I'm just writing expressions. Just writing expressions. I'm not looking for calculations. Yes, you know. I know you do, but you see nothing.
Oh yeah, it takes two of us. Oh yeah, that makes sense.
These two people got something, but I can't see in the middle, so. All right. What is the point on R? So that red curved graph on the left, what is that graph about? What does the point on that graph represent? Like the point that I've highlighted there. So right there. What does it mean? Yeah. What's that? Steepness. Is that what that means?
That's what specifically it is.
What's that? The what? The rate at the left of that interval. The point on the red graph means the rate at the left end of the interval. 1.5 to 2. Okay, right. So what's the value of x I'm showing here? At 1.5, what, miles from the border? It's telling us that there's some rate of change of elevation. That's what that point means. At 1.5 miles from the border, there's some rate of change at which the elevation is changing, and that's that value, something a little bit greater than 2. Okay? What about the blue points? So that's what a rate of change function is. Input is a certain quantity. Output, then, for each quantity is a rate of change of some other quantity. Okay? So in this case, we've got our input is miles from the border. The rate of change curve gives a profile of rates of change. Lots of rates of change for different inputs. Okay, what about the blue point? So I'm showing here at about 1.8. So what does that blue point represent? Okay, a constant rate of change at a given interval. Okay, but still, the point is just for one particular x value, in this case about 1.8. And what's the output? Is it a rate of change or an accumulation? Rate of change, okay. That's constant for that interval, right? So that's constant for that interval, whatever that is, about something close to 2. But just the point would be the approximated rate of change at a particular miles from the border. Approximated rate of change, particular miles from the border. What about a point on this graph? What's the black point represent? Okay? Points on graphs are always two pieces of information taken together. Points on graphs are always two pieces of information taken together. So, at a particular miles from the border, it's the elevation, or actually elevation change from the border. So if we're starting at 0 here, that means that's the border, whatever the border's elevation is. So that output of that function, or the y-coordinate of that point, will be the change in elevation from the border. But points on graphs are always two values taken together. Two values taken together, and then a graph is then many, many points, showing the relationship of those two quantities. Okay, express the change in elevation from 0.8 to 2.2 miles from the border. in two ways, using S and using A. So this is, like I told you there, this is K1, K2, K3, constant rates. So how would we represent the change in the border from 0.8 to 2.2 miles? I was hoping everyone could do this, but it was much more closer to no one could do it. Or they just didn't want to try and think about it. Okay, so how can we express the change in elevation from 0.8, which is right here, to 2.2, right here? Yes, sir?
You do K3 times the change in x, which is 0.4.
K3 times the change in x, 0.4, good.
Then K4 times 0.4, and K5 times 0.4. And then K6, since it's cut in half, would be K6 times 0.2.
He wants K5 times 0.4 plus K6 times, not a full delta x, right? So at halfway through the interval. Right, so to get little bits of accumulated elevation, we'll take the rate of change times a little change in number of miles. Good. What's another way to express that? What is it? Who was saying it?
A of 2.2 minus A of 0.8.
He wants A of 2.2 minus A of 0.8. That or something different? Divided by 2.2 minus 0.8. We divided by 2.2 minus 0.8? Because that's the formula we had before, so that must be it, right? Got it. Must divide by 2.2. What's the meaning, right? What's the meaning? Do I want a rate of change or just a change in elevation? I want a change in elevation. So A of 2.2 is something up here. A of 0.8 is something down here. So I want a change in elevation, right? I don't divide. I just want to know how much did the elevation change. We just summed up a bunch of little changes in elevation. And another way to do that would be to take the final elevation at 2.2 miles minus the final elevation at 0.8 miles. Okay, so those are the two ways you can express that. All right, so now I want to make delta x 0.004. So now on the left, that is still the graph of capital S. That's still the step graph, but now delta x is 0.004. But in general, this is representing a very, very, very small delta x. Okay? And then the resulting new graph over here, rather than calling it capital A, I'm going to call it capital E. Because it's a different kind of function. Okay? It's a different kind of function. So now I want you to express the change in elevation, same change in elevation, with this very, very small delta x. Who can do it? Who has learned something in calculus? Go for it. Express the change in elevation in two different ways, the same, over the same mile, from 0.8 to 2.2. This is what we said.
Yeah, they're kind of just like a stretched out S kind of.
Okay, I'll give you a hint. You do not use, even though I'm showing you the capital S function for 0.004, you're not going to use capital S to do it. Okay? That's a hint. Keep working.
Yeah, so you would use the same. I mean, it could be the same thing. Yeah, so snap is right there, but step are really small, so it's almost blending it to actual rate of change.
Okay, show me what you wrote. So 2 ways. 2 ways.
He changed the rate, see that? But still, it's gonna use 8. I mean, you could do that. That's what you step That one was just, like you said, it's more
Yeah. I don't think.
Okay, lots of you had integral, okay? So integral from 0.8 to 2.2, that's the easy part. So the question is, what are we integrating? I saw S, I saw E. What is it? Exact rate function, which in this case is R.
But it can't be a X.
Well, it can be if we have both numbers there. It doesn't matter what we choose. Okay? So R of X, just R of X? So just like we had rate times change in X, how do we represent that when things get really small? So, yeah. So Rx dx, or Rt dt. So because we have values in both places here, we can choose any symbol we want, okay? But that's one way to express that. It's an exact change in elevation from 0.8 to 2.2. And then, how else can we express it? No, not with sigma, because these are really, really small. Very, very small. So what's the other way we can represent this now? It's the same thing we had before here, but instead of the piecewise linear approximating accumulation function, this became E. So this became the exact accumulation function. So we can do E of minus E of 0.8. Okay, so next task. So I'll write that down again. It was the integral from 0.8 to 2.2 of r of x dx. And that's the same as? Is there a question? Anybody have a question? So now, write two versions of a function that outputs the change in elevation starting c miles from the border to any chosen number of miles from the border x. So the input of the function. Okay? So write two versions of a function that outputs the change in elevation starting, say anywhere here, say c miles, to any changing x. So c is we pick c and we keep it fixed. But then we want a function of, so the change in elevation as a function of where we stop. Say where we stop on the road, okay? So that can vary. So x is the input. And if we want, we can call that, say, we call it f of x. Okay, two different versions of this function f of x that gives us the change in elevation starting c miles from the border to any stopping location x miles from the border. Okay, hopefully we got that. What would it be? Nick, did you get it?
Yeah.
Tell me. Integral?
Yeah, integral c to 1 x.
From c to x of?
R of x dx.
Okay?
Equal to e of x minus e of c.
How do you do? One thing we got to change, right? So x we want to be the ending point, right? So therefore this won't work as x. Remember that? Because why do we need a different variable there? So we need to track all the values of x from c to x. And so we need a different variable that means tracking all the way, starting at c, all the way to x. Because x necessarily means only that x value at the end. And we know that the German S integral means accumulate all those bits of change, starting at c and ending at x. So we need that another variable that ticks us along one by one. Otherwise, that will just be a constant rate. The constant rate that at the end of the interval. Okay, so here's that same thing again. So this is our open form accumulation function. And when we have this function f, oh shoot, I forgot to, that's the most important question. So thinking about what we had on the previous page, where am I? What we had, we called it E, right? Is this what we had? How are the functions R and E related based on what we've been doing recently? How are the functions R and E related based on what we've been doing recently? I'm hearing that you're saying that R is the rate of change of E. Is that right? What does that have to do with what we've been doing recently? So all these rules that we've learned, right? That's what we've been doing. We took all these, learned all these rules for derivatives, right? So Rx is the derivative of Ex because a derivative gives us the rate of change function, right? And we'll pick it up there Wednesday.